Hello friends, I welcome you in lecture number 6 on relations. In this lecture we are going to discuss antisymmetric relation. This is also one important property of binary relation. So first we understand the definition of antisymmetric relation. Suppose we have some relation R on a set A, that is R is a subset of A cross A. Then this relation R is said to be antisymmetric on set A if whenever AB belongs to R and BA belongs to R, then this must implies that A equal to B. If AB belongs to R and BA belongs to R, then A and B must be equal. What is meaning of this? If we consider negative statement of this, then we can say that if A and B are different, then either AB belongs to R or BA belongs to R. If we have two distinct elements A and B in a set A, then either AB is present in R or BA is present in R. That means if A and B are different, then AB and BA both cannot be present in the relation R if your relation is antisymmetric. And this is another way of writing the definition, that if AB and BA both are in our relation, then they cannot be different, they are always equal. So either we can consider this as a definition of antisymmetric relation or this as a definition of antisymmetric relation. So we understand with the help of example. Here I have written that definition. A relation R on a set A is called antisymmetric if whenever AB belongs to R and BA belongs to R, then A equal to B for all AB belongs to A. This means a relation is antisymmetric if and only if there are no pairs of distinct elements A and B with A related to B and B related to A. In other words, if A and B are different, then either A is related to B or B is related to A. This both thing cannot happen at the same time if we have distinct elements A and B. In other words, the only way to have A related to B and B related to A is for A and B to be the same element. So again we repeat, if AB and BA are present in R, then A and B cannot be different. In other words, if A and B are different, then either AB is in R or BA is in R. So this is definition 1, this is definition 2, both are equivalent and we will use them in whatever situation, whatever definition is comfortable. If it is comfortable to prove using this definition, we will use this definition, or we will use this definition if it is comfortable to prove or disprove using these definitions. So here I have taken this set having 4 elements 1, 2, 3, 4, and I have taken some subsets of A cross A. If I denote this by set A, then I have taken relations on A, that is I have taken subsets of A cross A, and we will check whether they are symmetric as well as we will check that they are antisymmetric or not. And we recall the definition of symmetric relation. Symmetric relation is that relation which satisfies this condition. If AB belongs to R, then BA must be in R. And in antisymmetric relation, if AB and BA both are present in R, then A and B cannot be different. But be sure that these two definitions are not opposite of each other. You can have a relation which is symmetric as well as antisymmetric. So be careful that definition of antisymmetric is not opposite of the definition of symmetric relation. For example, suppose I consider a set having two elements 1, 2, and I consider this relation R equal to 1, 1 and say 2, 2. Then this relation is symmetric because if we change the order of elements, they are present if we change the order of elements. And this relation is antisymmetric also because if we have two different elements A and B, then we have to check either AB belongs to R or BA belongs to R. But here there is no such pair in which A and B are different. So this relation is symmetric as well as antisymmetric. So be careful, symmetric and antisymmetric are not opposite of each other. Now we try to decide whether some relations given on this set are symmetric, and we also check whether they are antisymmetric. So first we check for symmetry. So for symmetry I have to check that if I have AB belongs to R, then BA belongs to R. So if A and B are equal, this condition is automatically satisfied. So I don't have to check for 1, 1, 2, 2 and 4, 4. If we reverse the order here, we will get the same element. So that is present in your relation. Now I start with this element 1, 2 belongs to R1, and if I reverse the order, 2, 1 is also present in R1, and same thing here. If I change the order 2, 1, then I will get 1, 2, and that is also present. What about this 3, 4? So if we change the order here, we will have 4, 3, but that is not present in R1. So here I have to write that 3, 4 is present in R1, but if we change the order of elements, we get this 4, 3, and for symmetric relation it also must be present in R1, but it is not present in R1. This implies that R1 is not symmetric. Now we check for antisymmetry. For antisymmetry, we have to check that if we have A and B are different, then AB and BA both cannot be in our relation. So either AB belongs to R or BA belongs to R. Here also there is no problem if these two components are same. So we don't have to check for these three components. Now here we can see 1, 2 belongs to R1 and 2, 1 is also in R1. So 1 and 2 are different, and 1, 2 and 2, 1 both are in R1. So that is not satisfied. If we consider that definition, that if AB belongs to R and BA belongs to R, then we must have A equal to B. So here 1, 2 belongs to R1, 2, 1 belongs to R1, but 1 and 2 are different. So therefore R1 is not symmetric. Or we can use this definition also. If A and B are different, then either AB belongs to R or BA belongs to R. So here 1 and 2 are different, but 1, 2 and 2, 1 both are in R1. So R1 is not symmetric. So we can write in any way. We can write that here 1, 2 belongs to R1 and 2, 1 belongs to R1. So we are using this definition, and that definition says that if AB and BA both are in R1, then A and B must be equal, but here 1 and 2 are not equal. This implies that R1 is not antisymmetric. So we can see this relation R1 is that relation which is neither symmetric nor antisymmetric. So that implies that symmetric and antisymmetric are not opposite of each other. Now we come here for R2, we don't have to check for 1 1, and for symmetry we have to check that 1 2 belongs to R2 implies 2 1 belongs to R2. So we can easily write that R2 is symmetric. If we change the order of elements, then resulting element is also present in R2. Now what about antisymmetry? So this implies that R2 is not antisymmetric. Same reason, 1 2 and 2 1 both are present in R2. 1 2 belongs to R2 and 2 1 belongs to R2, but 1 and 2 are different. So here R2 is not antisymmetric. Relation is antisymmetric if AB belongs to R and BA belongs to R implies A equal to B. So here 1 2 belongs to R2, 2 1 belongs to R2, but 1 and 2 are different, so R2 is not antisymmetric. Now we check for R3. Again we consider 1 1, 2 2, 3 3 and 4 4. So there is no problem for this type of elements for symmetry as well as antisymmetry. Now I have to check first for symmetry. So 1 2 belongs to R3, and if we change the order, then 2 1 belongs to R3. So that condition is satisfied for this element. Now 1 4 belongs to R3. If I change the order, 4 1 is also in R3. So this means R3 is symmetric. And we can write that 1 4 and 4 1 both are present in R3, but 1 and 4 are different. Similarly, 1 2 and 2 1 are present in R3, but 1 and 2 are different. So R3 is not symmetric. 1 4 belongs to R3 and 4 1 belongs to R3, but 1 and 4 are different. Therefore R3 is not antisymmetric. I have taken some more examples also. Here I have taken this relation R4. Now I check for symmetry first. So if I consider this element 2 1, if I reverse the order, I must have 1 2 belongs to R4, but that is not present in R4. So we have obtained one element 2 1 in R4, but if we change the order of components, resulting element 1 2 is not present in R4. Therefore R4 is not symmetric. Now we check for antisymmetry. For antisymmetry, here I have 2 1, 1 and 2 are different, but 1 2 is not present. Now I check for this, 1 and 3 are different, so I have to check whether 1 3 is present or not. So 1 3 is also not present. 3 2 belongs to R4, so I have to check whether 2 3 belongs to R4 or not. So 2 3 is not present. Similarly 4 1 belongs to R4, but 1 4 is not in R4. 4 2 belongs to R4, but 2 4 is not present in R4. 4 3 belongs to R4, but 3 4 is not present in R4. This implies that R4 is antisymmetric. So here we can write that here A not equal to B implies either AB belongs to R4 or BA belongs to R4. That is, we have different elements A and B, then these two both are not present in R4, and therefore for all AB belongs to given set A, which is 1, 2, 3 and 4. So therefore R4 is antisymmetric. R4 is antisymmetric. So in this way we can check for this relation R5 also, and for this also. Suppose I want to check for this R6 equal to 3, 4, then we can easily say that this is not symmetric because 3, 4 belongs to R6, but 4, 3 is not present in R6, therefore R6 is not symmetric. And here 3 and 4 are different, and 4, 3 is not present, so here R6 is antisymmetric. So in this way we can decide for symmetry as well as antisymmetry. You can check for this relation R5 as a homework, and you can check whether antisymmetry is there or symmetry is there. So in general, remember this definition: relation is said to be antisymmetric whenever AB belongs to R and BA belongs to R implies A equal to B. In other words, if A and B are different, then either AB belongs to R or BA belongs to R. You can use either this definition or this definition, both are equal. In other words, we can say in this way also: if A is related to B and B is related to B is related to A, then A and B cannot be different. And if A and B are different, then either A is related to B or B is related to A. And for symmetry, we are familiar that if we change the order of components, then resulting element must be there in the relation for relation to be symmetric. So this is all about this session. Here we have explained how to check whether given relation is antisymmetric or symmetric, and in upcoming lectures we will continue with these properties of relations. Thanks for watching.